this video, we'll talk through the atomic spectra topic from Unit 1 of Advanced Higher Chemistry. By the end of this video, you should be able to explain the difference between absorption and emission spectroscopy, be able to use spectral information to identify elements present in a substance, and describe how a calibration curve is made. Start off talking about absorption and emission. Electromagnetic radiation can be absorbed or emitted, so it can be taken in or it can be given out by a species. You absorb radiation, you're going to increase the total energy, whereas if you emit radiation, you're going to decrease the total energy. Energy that can be emitted or absorbed is done in certain fixed quantities. Start off by looking at absorption spectroscopy. What happens here is that a sample is exposed to light and certain wavelengths of light will be absorbed by the species. And this is going to provide energy to promote electrons into higher energy levels. We then look at the spectrum, we can see which wavelengths have been absorbed. Different substances will absorb different wavelengths of light. And by looking at the spectrum, we can determine which chemical or chemicals are present in our particular sample. So we'll have light that's been absorbed at different colours within the visible spectrum. When we're talking about emission spectroscopy, light from certain wavelengths will be given out or emitted as the excited electrons drop down from a higher to a lower energy level. We can then have a spectrum where it shows which wavelengths of light have been given out. And a lot of the times these will correspond to visible regions. We're talking about flame testing, where particular chemicals give off particular colours of light. There will be times where it's the UV region that's being emitted at, and you have to use different pieces of equipment to determine that. We can use the sample to not only tell us which chemicals are in it, but we can actually look at how much of a species is present in the sample. By looking at how much light has been emitted or absorbed, that's going to be proportional to the quantity of the chemical in the sample. So if we have more light being emitted, then we've got more of the substance present in our sample. In terms of the questions that we can be asked about, we can be asked to look at a particular spectrum for either an emission or an absorption spectrum. With this question here, what we've got is an emission spectrum for hydrogen. When it's talking about emission, we're going to remember that that's to do with losing energy. And it's losing energy because the electrons are moving from a high to a lower energy level. Based on the information that we've got in our answers, the answer that corresponds with emission spectrum is D, where we have an excited electron dropping to a lower energy level, releasing a wavelength of light. This question is asking you to use the data booklet to find information that will help you determine which of these chemicals emits radiation of the highest frequency. And the data booklet will tell us information about the wavelength, and the frequency is inversely proportional to its wavelength. This means if we're looking for the highest frequency, that is looking for the lowest wavelength. We can look in the data booklet on page 16, which has the spectral lines and the flame colours. We're given the values of the wavelengths that corresponds to each of the different metals within the samples, and we're looking for the lowest wavelength, which makes the answer B for this question. Next kind of question is actually looking at the practical uses of absorption spectroscopy, where we're determining the concentration of an ion. First two options are talking about wavelength and frequency, and that depends on which ion we are analysing. So you have different wavelengths, which in turn means a different frequency if we're talking about sodium versus potassium, for example. We're then talking about absorption spectroscopy. We're looking at the intensity of radiation that's absorbed by the sample. In this type of question, we're asked to look at not only about emission versus absorption, but also looking at whereabouts in the electromagnetic spectrum we are focusing on. In this question, because we're talking about discharge is to do with giving out energy, which is going to be emission, which means we can get rid of the answers talking about absorption. We're then talking about producing a red glow. And we are seeing red glow because they're giving out red light, which means that we're going to be having an answer of B as our correct. answer. So in emission spectroscopy, we see the colour of light given out by the sample. With this question, we're again given a spectrum. We're asked this time to find out which line corresponds to red colour, but we're given the frequency. To do this, what we need to focus on is the fact that the data booklet tells us about wavelengths of light. On page 19 of the data booklet, we have the colour wheel, which shows us that the red end of the visible spectrum is between 605 and 750 nanometers. The fact that we're looking for one of the longer wavelengths means we're looking for a low frequency. To prove it, to make sure that we have got the correct answer, what we can do is use the relationship that wavelength equals the speed of light divided by the frequency. We plug in the numbers, and we'll start with the 4.6 one, because that's the lowest frequency in the question. So we do 3 times 10 to the power of 8 divided by 4.6 times 10 to the power of 14. That gives us our answer initially in meters, convert it into nanometers, and then the 652 nanometer fits within the range we want, which means that the answer is the line at a frequency of 4.6 times 10 to the power of 14 hertz. If we prepare samples of the chemical we're investigating at different concentrations, then measure the absorbance at each of those concentrations, we can take that data and turn it into a calibration graph. By plotting the values of concentration against absorbance, we then have a curve that we can use to determine the concentration of our unknown sample. We look at our unknown sample and we determine its absorbance. We can then run the line across to our calibration curve and then down, and we can determine that in this case, if the sample had an absorbance of 0.50, we would have a concentration of 5 milligrams per litre. In a question you might be given the calibration curve initially, they give you information about the unknown sample. In this question, it's telling us that the absorbance of the solution was 0.25. It also tells you about the volume of the sample that was being investigated. And this question wants us to calculate the mass of manganese contained within the sample. We're dealing with the calibration curve. The best thing to do is to read our concentration from our calibration curve. We have 0.25, so again, we run that across and we run that down. And that comes out as 1.4 times 10 to the minus 4 moles per litre. Question has given us information about the volume, and if we use N equals C times V, we can work out, so our number of moles is 1.4 times 10 to the minus 5. We are asked about the mass of manganese that's contained within this. For manganate is MnO4 to the minus, and within that we have 1 mole of manganese. Therefore, we can determine that we have got 1.4 times 10 to the minus 5 moles of manganese. Then, to work out our mass that's present, we're doing N times GFM. Number of moles is the 1.4 times 10 to the minus 5. Use the data booklet to find that the GFM of manganese is 54.9. We get our mass of manganese contained within the sample as 7.686 times 10 to the minus 4 grams. Hopefully by the end of this video you're now more confident in explaining the difference between absorption and emission spectroscopy, using spectral information to identify elements present in a particular substance, and also more familiar with how a calibration curve can be first of all created and then used to determine the concentration of a substance. Thank you for watching. Goodbye.